in a newly evolving area. Now it is, I would say it is one of the established area in mathematics is tropical geometry. So Hannah did her PhD under the supervision of leading algebraic geometer Andreas Kathmann. He does not require any introduction. And let me just tell you, even Hannah Markwig does not require any introduction either when we talk about the tropical geometry. So I was talking to someone and someone mentioned, who is coming from the tropical side? I said, Hannah Markwig will be giving the lectures on tropical geometry. So the person said, okay, so you got the queen of tropical geometry. So Hannah is coined as the queen of tropical geometry. And let me just tell you that this is one of the area which was introduced with the collaborative work of Bernard Strumpfels. And Hannah Markwig is one of the leading tropical geometer at the moment. And she has developed, and I would say she has translated a lot of interesting result from algebraic geometry to tropical geometry. And still many exciting work is going on. Almost all the celebrated results, almost all, from algebraic geometry has already been translated into the language of tropical geometry. And we are, I think we are in a phase where we started seeing some groundbreaking discoveries which are coming from the techniques of tropical geometry. And tropical geometry, Hannah is very good with discussing the algebraic, combinatorial, computational, all the aspects of algebraic geometry, but in a very different way, tropical geometry way. So over to you, Hannah.
Many thanks for this very kind introduction. I'm happy to be here. It's a pleasure to be at this school. So I wanted to share my pad here. Would you allow me to share the notes from my pad? So far, it only says the host has to allow.
Now you can do that.
Thank you very much. Oh, no, it doesn't. So I'm logged in with two things. One,
yeah,
so
we
that you
allow
can
the
see
second
me.
one too. Now you can do from both.
Great, fantastic. It works. Thank you. Okay, so let me start with some motivation. So I want to give introductory lectures to tropical geometry. And what's the motivation? We sort of heard it already in the introduction. We have algebraic varieties, which we think of, just as zero sets of polynomials. And there's a way to degenerate them. And this degeneration is called tropicalization. And then we obtain the so-called tropical varieties. Is the sound being okay for you? Because I have this problem that I hear some things twice.
Yeah, everything is okay. I think there's an echo. Okay, Hannah, you need to mute your second device so that the voice will come from only one device. Yeah, speak again.
I'm trying to do it, but I don't know how.
So one device should be muted and the other one should be allowed.
Well, muted it is, but I don't know how to stop the how's it called? Give me a moment.
Now it's okay. Try to speak something. Unmute yourself kindly.
I don't know why this was muted now, but now it
Now
seems
it's okay.
right?
We can hear you. We can hear you.
Okay.
Continue, please.
Very good. Sorry for this technical trouble. Okay, right. So we degenerate algebraic varieties to so-called tropical varieties. And tropical varieties you can just think of as certain polyhedral complexes. That satisfies certain conditions I don't want to specify. And then the idea is that this way of degeneration allows to use methods from polyhedral geometry or from combinatorics to prove theorems in algebraic geometry. That's all, vice versa. That's also possible, actually, that we can use techniques from algebraic geometry to prove things about polyhedral geometry. So for us, we'll mostly discuss curves, and dimension is preserved under this degeneration called tropicalization. So algebraic curves will correspond to just certain graphs. We'll specify this throughout the talk later, graphs that satisfy certain conditions. And now we can use methods from the theory of graphs somehow, or from combinatorics more generally, to prove theorems about algebraic curves. And more particularly, I will be interested in questions concerning counts of curves. So these are questions in enumerative geometry. So in enumerative geometry, what people do is they fix some geometric object, particularly, curves or plane curves of a certain degree and genus, something like that. And then they fix some conditions, like, for example, points in the plane through which the curves should pass. And of course, we have to choose the conditions in such a way that we have precisely a finite. Finite is the set of our objects satisfying the conditions, and not a higher dimensional family or so. And if we have such a finite set, then we want to count how many do we actually have. And such questions from enumerative geometry are very old, already ancient. In fact, the ancient Greeks asked questions. So there's the famous example about the Apollonius circles, for example. This, you can look it up on Wikipedia. It counts the number of circles in the plane which are tangent to 3 other circles. And there are 8. That's a beautiful picture you can see on Wikipedia. And as the name already suggests, this goes back to an ancient Greek called Apollonius. So even back then, people asked questions in enumerative geometry. But also nowadays, enumerative geometry is still a very active research area. And one reason why this is true is that many of those problems are very easy to pose. So everyone understands the problem and finds the problem interesting, but they're very hard to solve. So we'll get to know some of such enumerative invariants which were unknown for decades, for centuries, in fact. And so since around 2002, when tropical geometry was born, you could say, tropical geometry was also proved to be very useful as a tool in enumerative geometry. And that's what I want to show you with this talk. So that's sort of the message of this course. Tropical geometry is a successful tool for the study of enumerative problems. I hope that at the end of the course, this sentence will make sense for you, and that you will agree and like tropical geometry, in particular as a tool for the study of enumerative problems. Okay, so that's where we want to be at the end of the course. How do we start? Well, first I want to really just introduce tropical geometry, and I want to restrict to plane curves. So I want to, somehow it doesn't work to trash what I wrote. I'm sorry, technical issues. I press this thing, but it doesn't do anything. Oh, wow. It really doesn't do anything anymore. Writing I can still, huh? No. Oh, great. Okay. Maybe the pen just died. I loaded it earlier, but who knows? Haha. Okay, so now that worked. So let me hope that the pen is back in just a bit. So I want to introduce tropical plane curves because yeah, many of those enumerative problems are about plane curves, and it makes a lot of sense to restrict to plane curves, I think. And I introduced tropical geometry as this degeneration from algebraic geometry. I told you that tropical curves are degenerations of algebraic curves, but I don't want to define them like this now. I want to define them somehow purely tropically, intrinsically tropically, because I think that this is the more natural approach, that this will be the easier way to get into the subject. And then once we introduce them, we will see why those things are actually also degenerations of algebraic plane curves. So for the moment, these first steps may seem a bit artificial, but you will see how they connect to algebraic geometry in a bit. So I hope that you're happy to accept such an artificial start. We'll start by defining the tropical semi-field, because you can also introduce those graphs, which are degenerations of algebraic curves, those tropical curves, as curves over the tropical semi-field. So the numbers we need to use are R union minus infinity. And then we have, as usual for ring, two operations, plus and times. And plus is defined to be the max, and times is defined to be the sum of two elements. And it's easy to show that these operations are associative, distributive, and commutative. The neutral element for multiplication is 0, of course. Multiplicative inverses are just usual additive inverses. The neutral for addition is minus infinity, but we do not have additive inverses. This is the only ring axiom or field axiom, in fact, which does not work. There do not exist additive inverses. So if we write down an equation of the form x plus a equal minus infinity for some fixed a in R, and we want to solve for x, then this doesn't work, right? Because that would mean the max of x and a would have to be minus infinity, but a is some fixed number in R already, so that doesn't work. That doesn't make sense. Okay, so we cannot subtract tropically, but other than that, all field axioms are satisfied. Other than that, all field axioms are satisfied. Okay, and one thing I should mention right away, if you look into the literature and study some other tropical papers or books, you might find that people use min instead of max. So I would say that the literature is sort of half-half at this moment. There are good reasons for both choices. They are isomorphic, it doesn't really matter. People just make a choice for the reasons they pick. Okay, so we want to study plane curves, and plane curves are zero sets of polynomials, right? So let's define what a polynomial is, and let's study with a tropical term. And a tropical term of a polynomial is sort of the same thing as a term is in the usual world, just that we're using tropical operations. So we have a coefficient, and then we have a variable to a power alpha 1, let's say, and then finally an nth variable to power alpha n. And you have to be careful that those powers are yet again tropical powers. So when I write x1 to the alpha 1, I mean that x1 is multiplied with itself alpha 1 times, right? And so on. So let me translate that to what those operations really mean. They mean sums. So this is a alpha plus, and then I add x1. Oops, sorry. And I add x1 alpha 1 times and so on. So this is the coefficient a alpha plus alpha 1 times x1 plus and so on up to alpha n xn. And so you can also write it as this coefficient plus the usual scalar product of alpha with x, right? And so that means such a tropical term, if I view it as a function, then it's an affine linear function with a rational slope. So this is an affine linear function with a rational slope. And with rational slope, I mean that this vector alpha I used here is instead to the n, because those powers we use for our polynomials, they are, well, if we do lower polynomials, they are in z to the n, maybe they are even in the natural numbers to the n, but they are not arbitrary real numbers, right? They are, yeah, at least rational. Okay, so we have affine linear functions with rational slopes, which are the terms of our tropical polynomials. And now what is a tropical polynomial? Well, a sum of such guys. But when I say sum, of course, I mean tropical sum. So it's the max over some choice of alphas. And then, you know, some expression of this form. A alpha, the coefficient, times alpha 1 x1 plus and so on, plus alpha n xn. And so if we view it as a function, viewed as function from r to the n to r, this is now a piecewise affine linear function. A piecewise affine linear function. Let me do an example. Let's be univariate for the moment. So let's n be 1. We want to do curves in the plane. So the case we are most interested in is actually going to be n equal 2. But for those polynomials, it doesn't make much difference. So we can introduce them for arbitrary n, and we can make our examples first for n equal 1, because then the examples are a little bit easier to get started. So let's do something like the max of 1 x and -1 plus x. I see there's a question. The question maybe, sorry, let me look at it here. Is it a finite sum of tropical terms? Yes, absolutely. You're very right. Thanks for the comment. This is a finite sum. This notation wasn't meant to be about all alpha and n to the n. You know, you could also just let. So it's supposed to be about finitely many, a choice. Yeah, I should write it differently. Sorry. Just as usual. Just as for usual polynomial. We have a support. Let me write it like this. Yeah, so we have a finite support. We have a support of our polynomials. Okay, right, like in my example here, I take the max of 1, x and -1 plus x, so I have only 3 terms, a finite sum, as you said. Let's draw the graph of this piecewise affine linear function. Okay, so we have a constant function, 1. We have the function x, and we have the function, oopsie, that was a mistake what I wrote earlier. Sorry about this, -1 plus 2x I meant here. Okay, and so we start at like -1 here, but we have a deeper slope. Ha, I should have computed where the zeros actually are. Where do they meet? So the red and the blue line, they meet at x equal 1. Okay, and if x equal 1, then we are here already at -1 plus, then we meet the same thing, right? Because -1 plus 2 is 1. So the green guy also meets right there. Ah, sorry about that. Now here we go, the green guy. That's -1 plus 2x. Okay, but now we take only the max, right? So the max is this part. Yeah, so we can see that the blue term actually doesn't play any role. Well, it does take the max at a point, but this is a point where also the other functions take a max. But anyway, this is an example for such a univariate polynomial. And now I want to make another example where still n is 1. But I want to study cubic polynomials. And I want to study cubic polynomials in some sort of generality. So I want to write an arbitrary polynomial, a times x cubed plus b times x squared plus c times x plus d. And I want to make some assumption, which is that d minus c is less than or equal to c minus b is less than or equal to b minus a. And then I can make a similar sketch. We have a constant d wherever it precisely is. We have some linear term c plus x. We have some quadratic term b plus 2x. And we have a very steep cubic term a plus 3x. And now if you compute where those functions meet, you see precisely those numbers that I wrote down. So this is d minus c, and this is c minus b, and this is b minus a. And so you see that my assumption about the relation of those numbers means nothing else but that those corners are all visible, right? If we do the max now, this is the function we see. And so I'm assuming that it has those 3 corners. Okay, and now you can check some factorization of our tropical polynomial, you can check that you can write this tropical polynomial viewed as a function as a times x plus b minus c times x plus c minus b times x plus b minus a. Okay, maybe we should just convince ourselves by doing one case, like for example, if x is less than d minus c, then, well, a is still a, right? And then the maximum of x and d minus c would be d minus c, right? Because x is smaller. And then for the next summand here, the maximum of x and c minus b would be c minus b, because x is even below, x is somewhere here right now, it's below d minus c, in particular, it's also below c minus b. So for x less than d minus c, the sum here would be a plus d minus c, c minus b plus b minus a. And so many terms just cancel away, and what we obtain is d. And on the other hand, if we look at our cubic polynomial, the way we wrote it here upstairs for x less than d minus c, you can also just check that you obtain d. I mean, you can also see it from our graph, right? We obtain d here. And now you could go through all segments that we have and convince yourself that this equation is actually true. Your polynomial, your cubic polynomial, factors into tropical linear polynomials. So why did I show you this example? What do I want you to take away from this example? That is that those corner loci are like the roots of my polynomial, right? Because if like in the usual world, let me just make some small space here before we erase everything and start a new topic, so to say. So in the usual world, if I have a univariate polynomial, which, you know, could be a cubic polynomial, ax cubed plus bx squared or so, and I'm able to write it as linear factors, right? Then those are the roots of my polynomial. Yeah, so this is old world, old-fashioned polynomials. But the same thing is sort of true for our tropical polynomials. We can factorize our tropical polynomials into linear factors. And the values we have here for our linear factors, they are considered to be the roots of our tropical polynomials. And that motivates the next definition, which is a very important definition, which is about tropical hypersurfaces. What's a tropical hypersurfaces? Assume f is a tropical polynomial in n variables, let's say. And then we define the tropical hypersurface v trop of f to be the set of all points in R to the n, such that the maximum is attained at least by two monomials. And this is just another way of saying we're talking about the corner locus of the piecewise affine linear function f from R to the n to R. Okay, so the tropical hypersurface is a subset of R to the n. If you think back of my univariate example where n was 1, and I've drawn the graph of such a cubic polynomial, for example, then the tropical hypersurface would be those three roots, but in R, right? This would be an example of a tropical hypersurface. But what is more important for me, as I said, as I promised already, the case N2 is most important. And then, as also in algebraic geometry, when hypersurfaces in the plane are called curves, so those are called tropical plane curves. Tropical hypersurfaces in the plane are tropical plane curves. And here's an example in the plane. Let's take f to be the polynomial x plus y plus 0. So, let's write it as the max of x, y, and 0. And now you know why I started with a univariate polynomial, because drawing a graph would be much more complicated. Now I have to draw my graph in 3 dimensions, but I don't think I want to do it. Let me just sketch the plane and show you what's happening for this function, right? So, we can also just equate 2 of those terms and set them to be the maximum, right? What can be? It can happen that x equals 0 and is the maximum. That is this ray here. I should use another color so that you can see better. This ray here, right? Or y is 0 and the maximum, that's this ray here. Or x is y and the maximum, that's this ray here. So this is a linear polynomial. This is a tropical line, therefore. Tropical curve coming from a linear polynomial is called a line. So a tropical line consists of 3 rays that meet at a point. And the function, if we try to view the function, then the function takes value 0 on this cone here, value x on this cone here, and value y on this cone here. So if you insist on trying to draw this in 3 space, then it would be a picture that sort of looks like this, right? I hope the picture makes sense, yeah? So this part here is well, okay, I was lying. I was drawing the axis a little deeper. This is a z equal -1 if you want. Just drawing the axis a little deeper so that I can draw something at all. Anyway, I hope that you can see this function, and I hope that you can see this tropical 0 set, which is a tropical line. And one thing you could try is to play with the coefficients of my linear tropical polynomial in 2 variables. So why don't you study something like a plus b times x plus c times y and draw the tropical line for this. So this could be a good exercise if you have some time left at some point. And maybe one thing I should tell you already is that in any case, you will receive 3 rays. So your tropical lines will always kind of look like this. And the only question is, where is this point? Where is the vertex of the tropical line? Okay, so with this small example, I hope that you can see already that tropical plane curves have a lot of combinatorics behind them. And we want to discuss this combinatorics now in order to understand better what's going on here. So what we'll learn next is that tropical plane curves are dual to so-called marked Newton subdivisions. Subdivisions of the Newton polygon. So I want to start by showing you what is a marked Newton subdivision at all, and then I'll show you why those are dual. So here's the definition. Let Q in R to the n be a lattice polytope. Well, what does it mean? It's a polytope, and the vertices are lattice points, are points in Z to the n. And let's let A be the set of all lattice points inside my polytope. And let's A prime be a subset of A. And then QA prime, sorry, is a marked polytope. Is a marked polytope if A prime contains the vertices. And now what is a marked subdivision? A marked subdivision is a set QI AI, finitely many again, such that each QI AI is a marked polytope. The dimension of each QI is the dimension of Q. Q is the union of the QI, so this is really a subdivision. So there's more in saying that it's a subdivision. So that's saying that the intersection QI intersected QJ is a face of both QI and QJ. Could be the empty face, but it has to be a face. AI has to be contained in my subset A of lattice points of my polytope. And finally, AI intersected QI intersected QJ has to be the same as AJ intersected QI intersected QJ. Now let me draw some pictures so that those things make sense. So here's a polygon, a lattice polygon, triangle actually, with the vertices being lattice points, right? And I've also drawn all the lattice points, so I've also drawn the subset A. And now I can, for example, subdivide this somehow. I can subdivide this. And now what I like to do is sort of draw the lattice points white, which are not marked. So this would be a sketch. That means that I have a Q1 here and a Q2 here, and the marked points of both QI consist of precisely the vertices, yeah, because of this white vertex down there. So this is an example of a marked subdivision. And this fifth condition, that justifies that I can actually draw marked subdivisions like that, because this thing saying AI intersected the face QI intersected QJ is the same as AJ, means that, you know, the points Q1 intersected Q2 would be this edge here, for example, and AI are the points that are marked in Q1 on this edge, and AJ are the points that are marked on Q2 on this edge, and they have to be the same, right? But only if they are the same does it make sense to draw pictures like this. So marked subdivisions in general are, you know, subdivisions of polytopes, lattice polytopes, of course, that look somehow, and then they have some points are marked inside here and others are not. They look somehow like this. Okay, and how do we obtain a marked subdivision from a tropical polynomial? Well, two things. Given a tropical polynomial, first, we have the Newton polygon, or Newton polytope more generally. What's that? That's the convex hull of the exponent vectors. That's just, you might have heard it also for classical polynomials. So let me do an example. Let me pick f is 0 plus minus 1 times x plus, let me think, no, I want to take plus 1, plus 1 times y plus 1 times xy plus 2x plus 2y. Now I was mixing classical and tropical notation here. I should write x squared, of course, and here y squared. And let me remove the sign so that it doesn't confuse you. Okay, very good. So that's my tropical polynomial. And I can also write it as the max of 0, 1 plus x, 1 plus y, 1 plus x plus y, 2x, and 2y. Okay, so what are the exponent vectors? Well, 0 is x to the 0. 0 is the constant term, so it's coming from x to the 0, y to the 0. So we have the point 0, 0. X is x to the 1, y to the 0. So we have 1, 0 as exponent vector. Y gives us 0, 1. Xy gives us 1, 1. X squared is 2, 0. Y squared is 0, 2. So the convex hull of those exponent vectors is this triangle of size 2. That's the Newton polytope of my tropical polynomial here. Now, how do I get a subdivision? I use the coefficients. I haven't used coefficients yet, right? So far, I've only taken the exponents. Now we take coefficients. So let me write the coefficients next to the points. I have the coefficient 0 here. I have 1 here. I have 0 here. 1, 1, and 0. What we do now with those coefficients is that we put them in a third dimension and think of them as heights. So my Newton polygon is sort of lying on the table here. And these numbers here are heights in 3 dimensions. So this is again hard to draw, but let me try. Those 3 are of height 0, so they continue to lie on the table. And then I raise the other one to height 1. So, and now I look at the convex hull of this. So, you know, it sort of looks like a roof. And then what I do with this roof is that I project from upstairs. Yeah, I project what I see upstairs down. And then I hope that you can see that this triangle in the middle is certainly something I will see, because this is what I can see on the top height, right? And then, so on top height, I have this little triangle on height 1, and then the other triangle sort of fold over and produce this subdivision. And in addition, to obtain a marked subdivision, I mark the points which are visible on this upper convex hull of this extended Newton polytope, how it's called. So let me write something. We form the extended Newton polytope. By adding the coefficients of the tropical polynomial as heights, and then project from above and mark the points which are visible from above, which are not underneath this convex hull, but which are actually visible on the convex hull. So this is a way how to obtain a marked subdivision from a tropical polynomial. This is how to obtain a well-marked subdivision, or just let me just say subdivision from a tropical polynomial. Okay, and now I can formulate the duality theory. And this duality theory says that we'll formulate it only for tropical curves, just for the sake of simplicity and being explicit, but it holds for any tropical hypersurface. So, but let me just pick two variables n equal 2. So then I'm talking about plane curves. And then I take a tropical polynomial in those two variables. And then the plane curve, the tropical plane curve, v trop of p is dual to the Newton subdivision of p in the following sense. What does is dual really mean? There exists a vertex of v trop of p for every polygon in the subdivision. For every edge, there exists an edge. So let me just say edge correspond to edges, and they are perpendicular. And finally, a connected component. No, sorry, I have to write it differently. A connected component of R2 minus the tropical curve corresponds to a point, a vertex in the subdivision. Now I think an example or a picture says a lot more than all those words. So let me go back to the tropical polynomial we just studied and the subdivision it produced. So this tropical polynomial was, let me just write it directly as a max. The max of 0, 1 plus x, 1 plus y, 1 plus x plus y, 2x and 2y. And now if you play the game, admittedly it's a bit of work, but you can just play the game we played for the tropical line and try to set two terms of this polynomial equal and being equal to the max. And if you do this, you will obtain a picture that looks like this. No, I should use a different color so that you can see better. Oops, sorry. Didn't. Okay, once again, these are the x's. Now the different color, very good. So you obtain a picture that looks like this. This is going to be the tropical curve associated to this tropical polynomial. And now this vertex, let me call it V1, this vertex V2, V3, and V4. And this vertex corresponds to this Q1 here. This is Q2, Q3, and Q4. And you can see, so locally, what you see around this vertex is sort of the outer normal fan of this Q1. We try to sketch the subdivision a little bigger. So it's not always true that you can draw a tropical curve sort of inside the subdivision because of the length of the edges that the tropical curve may have. The subdivision is not saying anything about length, right? But what it says is so that here's a vertex and there are edges perpendicular. And here's another vertex, and again, edges perpendicular, and so on. And what I should also stress again is that these edges here, they are raised, they continue forever, right? I just can't draw this. They are raised, they continue forever. And the rays or the ends, they correspond to edges at the boundary. Right, so there's even more about duality that you can say. And on the other hand, each vertex here corresponds to a connected component of R2 minus the tropical curve. This vertex corresponds to this connected component, this vertex to this vertex to this, and so on. Yeah, so this is the duality theory. And the duality theory helps us to draw tropical plane curves extremely quickly. So before I said, you know, if I give you a tropical polynomial like this, what you have to do is you have to go through each pair of terms, set them equal to each other and figure out whether they can be the maximum or not. That sounds quite painful as a task, and it is, of course, but it is a lot quicker to just say, okay, let's first determine the dual Newton subdivision like we did in our example, and then we know how the combinatorics of the tropical curve looks like, right? Then we know that there must be 4 vertices and that those 4 vertices must be connected with edges somehow like this. All we don't know is how long those edges are, right? They could be long, they could be short. That is something that is not coming out from the dual Newton subdivision. But what we can do then is that we just compute the position of the vertices, because the vertices are going to be precisely where the terms corresponding to the polygon, which is dual, take their max. Yeah. So for example, V1 is at what? So what terms correspond to Q1? This is the constant term, 0. And then the x term, which is 1 plus x. And the y term, which is 1 plus y. So you set this all equal, you obtain x and y is -1, -1. That's the position of your V1 here. Yeah. Similarly for V2, for example, V2 corresponds to Q2. Q2 has those 3 terms here, the x term, the y term, the xy term. So the 3 equations for Q2 would be 1 plus x equal 1 plus y equal 1 plus xy plus x plus y. And you see that this holds precisely if xy is 0, 0. So that's the position where V2 is. So the duality theorem is extremely powerful because it tells us many things about our tropical plane curves. It tells us that they are very combinatorial objects. It gives us a way to draw them more quickly. And it also tells us more properties about those graphs. So what do we want to do? I mean, I started with those tropical polynomials, and I told you this may seem a bit artificial at the beginning, but we'll learn why those guys are tropicalizations, meaning degenerations of algebraic curves. But before we can make the step to understand why they are degenerations of algebraic plane curves, we want to understand what objects those tropical plane curves really are. And what can we deduce from what we learned so far, from duality in particular? We can deduce that tropical plane curves are graphs in the plane that are piecewise linear. All the edges have rational slopes. And those graphs also have those unbounded ends or rays, as you might call them. But the Newton polytopes also tell us that there's something more to be taken into account. So assume I have a polytope that looks like this, for example, and then I can look at the dual tropical curve, at a dual tropical curve. It will look somehow like this. And what are the directions of those vectors? They are orthogonal to my edges in the Newton polygon. So this vector will have direction 1, 1. This will have direction 1, -1. And this here has direction -1, 0. And now if you stare at those 3 vectors, you might see that if I insert a 2 here, then they sum up to 0, right? And that's a very attractive feature. That's actually called the balancing condition of tropical plane curves. And this 2, of course, has a lot to do with this 2 we see here, right? There are 2 steps in the Newton polygon that we have to take for this edge. So let me make this precise. Let me define the weight of an edge of a tropical plane curve. The weight of an edge of a tropical plane curve is the lattice length of the corresponding dual edge. Dual edge in the Newton subdivision. And then I can formulate the balancing condition. No, it works again. The balancing condition. Let gamma be a tropical plane curve. And V in gamma a vertex. For an edge E adjacent to V, let WE denote its weight. And now the pen died. I'm very sorry. To give me a couple of minutes to load the pen again. Let me continue speaking so at least you hear already what it's coming next. So WE is the weight of this edge, and PE we call the primitive integral vector pointing from the vertex into the direction of E. And then the sum of the WE's, PE's is 0. The weight, WE is the weight, PE the primitive integral direction. Pointing from V into this edge E, then the sum of the WE, PE is 0. And the idea of proving this duality theorem is precisely this picture that we saw up there. Let me make this a bit more detailed. Just have some space here. So in general, we have, some big Newton polygon, and we're talking about a vertex of our tropical curve. And this vertex corresponds to some polygon. Maybe it's only a sketch, right? Sorry. So this vertex V corresponds to a polygon Q in this subdivision here. And this polygon has edges. And the edges are perpendicular to the WEPE that I have here. Yeah, if I have, for example, like in my concrete picture up here, if I have an edge here, this edge here of my Newton subdivision, it has lattice length 2. And if I just turn this vector around here, orthogonal, then I get the vector 2 times 1 minus 1, 0, right? Which I used here in order to make this balancing condition work, namely that those vectors sum up to 0. But now the vectors which form the edges of my polygon here, they are a closed walk, right? Because they are the edges around a polygon. And so vectors that if you lay them one after the other and they form a closed walk, they meet again, then they add up to 0, of course. But then also the perpendicular vectors will add up to 0. And that is the reason why this balancing condition works. And so now we are ready to make a definition which
Markwig,
does not.
Excuse me.
Yes. Yes.
Yeah. We are already in time, so probably this is the time for the questions.
Okay.
Can you check the chat box first?
Sure. Can I just write down to sum up what we learned?
Okay, you can write.
1 minute. 1 minute to sum up what we learned. That would be so tropical plane curves. Weighted graphs, the edges have weights. Weighted graphs in R2. with edges of rational slope and also unbounded edges that satisfy the balancing condition. So this is what I'd like you to take away from the first meeting, the first course of this series about counting tropical plane curves. We view tropical plane curves as weighted graphs in R2 with edges of rational slope and unbounded ends that satisfy the balancing condition. Okay, now I'm ready to take all kinds of questions. Please go ahead.
Okay, firstly, can we go to the chat box?
I don't see any question in the chat right now, except the old questions.
Okay, these questions were already attended, I think. Are there any questions from the audience? Okay, for Professor Hanna, it was a bit quick for Penny because during the middle part, it was even difficult for me to keep a track on, particularly when he was defining the Newton polytope or then the subdivision. You have some question? So.
Sorry, you said that you're ready for any kind of a question. So this is merely asking you to repeat something you said about when we're constructing marked subdivisions from a tropical polynomial. So when you go from this Newton polytope, and so you said somewhere that coefficients will be treated as heights. And can you repeat the construction?
Absolutely, yeah, no problem at all. So, is it helpful to repeat the construction at a concrete example?
Yeah, absolutely. Maybe you can
Probably,
go back
right?
to what you've written up already and just make the second picture again.
Yeah. Let me just take a new example to see something new. Let me take the max of 0, 1 plus x, 2x, and x plus y. Okay, so first we look at the coefficient vectors. So, you know, what's a complicated, let me write this as a tropical polynomial first of all, right? So this is 0 plus 1 times x plus x squared plus x y, right? And so now we have 4 terms here. And what's a more complicated way to write these terms? 0 times x to the 0 times y to the 0, right? Plus 1 times x to the 1 times y to the 0. Plus, well, 0 times x to the 2 times y to the 0. Plus 0 times x to the 1 times y to the 1. Now we take those exponent vectors. These are the exponent vectors, and we draw the Newton polygon. So 0, 0, 1, 0, 2, 0, and 1, 1. That's the Newton polygon. It's triangle here. And now we take those coefficients and we view them as heights. So let me just write them next to here first. So this 0 belongs here. This 1 belongs here. Then we have another 0 here and another 0 here. And now it's the difficult part. Now we have to put this into 3 dimensions and view those as heights. Yeah, this is hard to draw. Let me try. This is height 1, height 0, and this is at height 0. So we get like, you know, like a tent. Yeah, you can imagine we take this guy and move it upwards. We get like a tent, and in particular, this tent has an edge here, and if we project downwards, we obtain this picture. And this is what is the dual subdivision for this tropical polynomial f. Does this example help to clarify the confusion also about the part where it was a bit quick? Sorry about that.
Yes, thank you very much.
Sure, you're welcome. Now I see
Thank you.
also
Thank
a
you very much.
question. No problem. Sure. I see a question in the chat which asks whether there's a relationship between probabilistic methods and tropical geometry. So that question, let me answer it shortly by just saying not yet. So there's really not much research trying to combine probabilistic methods and tropical geometry yet, but I think it could be a very interesting subject. Yeah.
Okay, one quick request is that please keep your writing speed a bit slow so that
No problem. Yeah.
anyone can copy and understand properly.
Sure,
I think there is one more question in the chat box.
There's one more question in the chat. That was the dimension of a polytope. Yeah, I'm totally aware. I haven't really defined what a polytope is. I was just hoping about the intuition that you have about polygons and polytopes. So, you know, these guys have dimension 2, and they are actually the only ones we need. We need polygons. Polygons are polytopes of dimension 2. Polytopes of dimension 2. It's just if you take the vector space, the affine vector space that is spanned by a polytope, then the dimension of that affine vector space is the dimension of the polytope. Yeah, so the dimension of such a cube, for example, is 3, right? I hope that answers the question.
I think so.
Very good.
Okay, so there is a request. Can you repeat that balancing condition?
Repeat the balancing condition. Yes, not a problem. Okay. Right. Let's actually maybe just take this example that we just studied. Now, a tropical curve dual to this looks like this. What I have to do is find out where the position of these vertices are, but let me not do this right now, because the balancing condition has nothing to do with positions. So what do? We take those vectors here. For one polygon, we pick one polygon. This is the polygon, this is the vertex, the dual vertex we study. And we have those 3 vectors. Those 3 vectors right now are 1, -1, -1, 0, and 0, 1, right? And they add up to 0 because they correspond to the edges of a polygon, right? So they form a closed path, and for that reason, those vectors have to add up to 0. And now the direction vectors of the edges around my vertex, they are precisely perpendicular, right? So I just take those and take the perpendicular vectors. Turn them around, always in the same, around the same anchor, right? And then they have to sum up to 0 also. And the only thing to pay attention to is that some vectors of those polygons, like for example, this is a different picture, this is a different example. Now I have only one polygon and one vertex. But now this edge is not a primitive vector. It has lattice length 2. Yeah, so it's 2, 0 or -2, 0. Yeah, and that corresponds to that in the dual picture. I should take 0, -2 as the dual vector spanning this edge, so to say, or let me write this as 2 times the primitive vector, 2 times 0, -1. And then this is what is called the weight. And this is the primitive vector in the direction. Primitive integral vector, I should say, has to be with integers, of course, otherwise it doesn't make sense. Primitive integral vector in direction of the edge. And the statement is now that at each vertex V, the sum of those weights times the primitive, E times the primitive directions. E is an edge. This is the weight of the edge. And this is the primitive integral vector. That this sums up to 0. So I have a vertex V, I have the edges around, and those vectors, they sum up to 0. That's the statement of the balancing condition, and also already the idea of proof by using the duality.
Thank you very much. I think now everything is clear. I hope, are
I'm
there any
glad.
other
Okay.
questions? Okay, I hope there are no. We would like to thank you once again for a wonderful lecture. And just a small announcement that we are going to post all the recordings of these lectures, which is delivered by Professor Hannah Markwig on our homepage of the event. Okay. Thank you, Professor Hannah. Thank you very much.
My pleasure, and I will see you tomorrow.
Now there are